Right, hi, thanks. I actually do have a pun somewhere in this talk, so if you spot it, that means you don't have any good humor. So I'm going to hopefully tell you about how our solar system, the place we live, fits into its galactic context. So some of you may not know that we now know of thousands of other planets around other stars. So we no longer have to just look at our solar system and make broad, sweeping statements about how frequent life is, Earth-like planets and anything. So I'll give you sort of a 15-minute introduction to this field, which is now 20 years old, so more than 15 minutes, so I can't cover it all. But so let's begin with our solar system. So some of you may have seen pictures like this before, with a ninth thing at the end, Pluto. I have left it off here, but you know, you can have your opinions. So for centuries, we have known everything up to Saturn: Mercury, Venus, Earth, Mars, Jupiter, Saturn. Even millennia. Only very recently have we added numbers 7 and 8, Uranus and Neptune. But even before Uranus and Neptune, even when we just had 6 planets, we didn't have technology, there were scholars sort of wondering, do these other points of light in the sky have other planets around them? And one of the earliest quotes I found was Giordano, yes, Bruno, I was sort of faking. This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own. He was burned at the stake for heresy, but hopefully I will not be. So the point is that he realized, looking into the blackness of space, it's almost infinite. It would be very, very surprising if there weren't other worlds out there. Why should we be so special? All right. So crucially, the same kind as our own. This same kind as our own has prompted me to let's look again at the solar system. What kinds of things might we expect other solar systems to or to not have? So first of all, here's the latest NASA photograph of the solar system. No, this is some really bad drawing of the solar system, and crucially, it's sort of flat. It's flat as a pancake. It looks like someone took a ball of dough and spun it out into a disk. And out of this disk, all the planets formed, inheriting the plane of whatever disk of material there was. Also, the star, the sun, is actually rotating with a period of about 30 days. So every month, the sun goes around once. And it's sort of pointing, it's spinning in the same directions as the planets are orbiting. So this very, very aligned state, very, very early on, prompted Immanuel Kant, 1755, to propose the idea that the solar system formed from big clumps of gas like this. This is a Hubble image from last year of the Eagle Nebula. And small regions here become very, very dense through perturbations or whatever, gravitationally collapse, and then it is this gas that spins out into a disk which forms the planet and the stars. So everything looked very nice, and then within this disk of gas, the planets form by big things bumping into other things, and so on and so forth. So there's no reason why this shouldn't happen elsewhere. Why, whenever other stars form, there shouldn't be planets around them too. But we've only been able to find planets around other stars recently because planets are really, really pathetic and dim. So we have to use tricks. And I thank John for these pens that we got earlier that light up, if you can. Okay, so imagine this is our star, and I want to see a planet around it, but the planet is way too faint to just look. Imagine if I held a flea here. You wouldn't be able to see it. The star is too bright. What we need to look for is a tiny wobble in the motion of the star from a planet that is orbiting it and sort of tugging on it as it orbits. Alternatively, so that's, didn't switch the slide. That's on the left here. That's sort of like a hammer thrower at the Olympics throwing around a big heavy weight, the hammer thrower himself will also wobble. Another way of looking for planets is the so-called transit, which is essentially when the planet goes in front of the star briefly, blocking the light and carrying on its way, and then the light of the star goes up again. So it is through a combination of these two methods that we've been able to peer at other stars and realize the galaxy is teeming with planets. There are thousands, literally thousands of planets we have found around other solar systems, as opposed to the 8 or 9 that are in our solar system. So these techniques were first successfully applied in 1995 when I was a baby. So the field of exoplanets is about as old as I am, which is nice. A little more important, but you know. So let's look at this for a second. It was discovered by Michel Mayor. So our solar system is on the top here, and this is to scale. So we have the Sun, we have Mercury, which is about a third of the Earth's distance from the Sun, which is 90 million miles. And this is the first planet that was ever found. It is 1/20th. Sorry? Oh. Apparently that message wasn't meant for me. This planet is 1/20th as close to its star as Earth is to the Sun. What's more, it's the size of Jupiter, and Jupiter is the largest planet in our solar system. It's a monster, about 1,000 times as heavy as the Earth. But this star has one of these planets like super, super close. And we call these things hot Jupiters because they're Jupiter-like and they're close to their star. This is a professor at Caltech like heating up planets and calling them hot Jupiters. So this was the first one, 1995. Since then, as I said, we have discovered thousands. Most were discovered by the Kepler Space Telescope, which looks for these transits, looks for the dip in starlight as a planet goes in front of it. So now we have enough. Was this hot Jupiter? Are they the typical? Do most solar systems have a really massive thing close to the star? Or was that just unusual? Because they're much easier to see because they tug much harder on the star, so they're easier to find. So as it turns out, that's not true, and I'll get to that in a second. But one of the more surprising features was that, remember when I said that the solar system was aligned like a plate, and the star, the Sun, was rotating in the same direction as it? Turns out this doesn't happen in other solar systems, and hence the sort of half of the title of my talk, Upside Down, Inside Out Solar Systems. This is the upside down. So a lot of solar systems don't look like ours. They have a star which is upside down relative to their planet. The planets seem to be going in the wrong direction. These are known as spin-orbit misalignments because the spin and the orbit are misalignments. So that's one surprise. And, you know, Emmanuel Kant won't like, here's the pun, this can't be. Thank you. So this is, so does this mean our solar system is already weird because it's pretty much aligned? Well, it turns out that this is actually more common around stars that are just a little bit more massive, a little bit bigger than our Sun. So our star is sort of normal in the galactic context, but in terms of what other options are out there, there are much more than just an aligned system. Perhaps if we had a system that looked like this, we never would have guessed that planets formed in a disk, even though they must form in a similar way. And actually, this is a field that I sort of work in, and I've sort of proposed, and it looks like the reason why the Sun is aligned with the planets, whereas these other heavier stars aren't, might be because the magnetic field of the Sun gripped onto the disk, shackling it to the same orientation of the disk 4.5 billion years ago when the planets were all forming. This kept everything aligned and kept everything orderly and looking like clockwork, which is the way we tend to see orbital mechanics today. Okay, so that's one surprise, the upside down. What about the inside out of my talk? So here's our solar system again. Here's Mars, Earth, Venus, Mercury. So what I'm showing here is the fact that inside of Mercury's orbit, there's enough room to fit 80 suns. There's no real reason why there should be nothing inside of Mercury's orbit. But, you know, if this was the only solar system you're ever looking at, you might not think twice about it. It's like, well, maybe it's too hot there, stuff just evaporates, the planets are blown to shreds. Okay, fair enough. But I have already told you that the first planet ever found was sort of here. It was way inside here. And now we have thousands we can ask whether that's normal. Turns out it's very normal. So these are all the examples of planets we have that are inside Mercury's orbit. Turns out about half of stars have a planet which is closer to its star than Mercury is. So it's already, our solar system is 50% weird at least. So this is the inside out. What's more is the most common size of planet in all of these systems is what's called a super Earth. It's a little bit bigger than Earth, a little bit smaller than Neptune. And there is no representative of this most common size class in our solar system. Or is there? Some of you following the news might have heard of these two characters here, Konstantin Batygin and Mike Brown. Mike Brown killed Pluto. Konstantin Batygin is my advisor. And Mike Brown was his advisor, so I don't know if there's any inheritance of like destroying planets. Maybe that's what I'm destined for. But so they have found that so here's the solar system you probably know. This isn't very clear, but this is like Neptune and Uranus out here. Outside their orbit is what's called the Kuiper Belt, however you want to pronounce it, Kuiper. And within here, the orbits of things are sort of strangely pointing in one direction. They kind of look like this. A bunch of them are swinging out in one direction. And this has been interpreted by Konstantin and Mike as the existence of a super-Earth, the most common planet size in other solar systems. Looks like we might actually have one. It just got thrown out, way out far into the other solar system. We haven't been able to see it yet, simply because it's just too far away. This really puts our solar system on the map in terms of having a planet in this size range that is the most common size range. So, what is our solar system's place? It's the right way up, which is common for stars of our size, the sun's size, not our size. But I like that. But it's not the only answer. It's not the only answer to how you form a planetary system, that everything is aligned. Also, about half of planets have stuff inside Mercury. We've got this big void of nothing inside Mercury. In fact, once people thought there was a planet inside Mercury called Vulcan, because it was so hot. Turned out it's not there, sadly. But most planets do have lots of Vulcans, and they're huge. They're bigger than the Earth. So planetary size, I already covered that. There's potentially a super-Earth outside, way out there. We'll wait for the observers to actually see it. So far, it's like the wind. You can only see it by its effect. But what about life? I don't like talking about life too much, but I don't like life. It's like, you know. But turns out we actually have a little bit of a handle on life as well, how common life might be in the universe. And my friend and colleague, Eric Pedagura, has found that about a fifth of stars of the same size as our sun have a planet that's about Earth size, that receives about as much sunlight as the Earth. So potentially a fifth of all stars have habitable planets, which puts our solar system in context. Maybe maybe a fifth of stars have another Chris Spalding talking about how weird this Earth system is. They find, i.e. life. That's my long way of saying might have life. So hopefully you learned something. Hopefully you enjoyed something. And thank you. John. So if I weigh like 200 pounds here, how much would I weigh on Super Earth? You wouldn't actually weigh that much more in Super Earth. Maybe 1.5 times. You know, you would need to go for a little bit of a jog, but You'd be fine. Yeah. Yeah. Very, very good question. How are scientists able to, and I'm a scientist, how are we able to tell the spin or the spin direction of the star relative to the planet? It's kind of subtle. So I said about the transit, the planet going across the front of the star. Turns out when the planet goes across, so if the star is going like this, it's spinning. So part of it is going towards you and part of it is going away from you. And you can tell when the planet goes across it, it blocks the bit that's going towards you and the bit that's going away from you separately. And just like the Doppler effect of a train going by, the side that's going towards you is it's higher pitched. And then the one that's going away from you is lower pitched, it's bluer or redder. And you can, I don't want to give too long, but you can tell from the way that you cover the right and the left side of the star what path it took across the star, and you get the spin from that. Thank you.